Hi everybody, this is my second live stream today, and I wasn't thinking I was going to end up doing this, but it so happens I've been doing my programming. I did some cool things that I want to share. So I'm going to share my screen so I can show you what I can do with computer programming with OpenGL and how it works the way it does. This is very freaky stuff. So it's time to screen share, and you should be able to see what it does here. So how about, let's see, I can leave myself on the side here so that you can still see. If only there was a way to like customize this more. Okay, anyway, so here's what's going to happen is I'm sharing my screen. Here you see I have a terminal. Actually, what I'll do, let's hide this little message here. I'll show you what I do. I'm running Ubuntu Linux. Okay, so I'm just going to close out of everything except for Google Chrome here. And then, okay, yeah, I need to hide that message. So here's what it looks like for me. So I go to my home folder here. I go to Documents, and then I go to the very special folder where I've been keeping my core OpenGL code. Now, core is the modern stuff. Legacy is the really old stuff. And I have a lot of stuff here. So here's what I have. So I opened this folder in terminal. And when I type make, it compiles and runs my code. And it's really amazing the way it works here. So you see there's a spinning triangle, and notice it changes. It changes constantly. Now, first of all, I'm going to press Z and stop it. I'm going to change it back to a triangle. So there's a few things I want to be able to show you here. First of all, I can change the size of this window. See, notice how the triangle changes. Like, it's weird how that is, because the triangle changes when I resize the window. It automatically recenters the triangle wherever it is. And that's because there's code behind everything. So when I try to maximize this, now we have this triangle here, and I can move the triangle around. This is really incredible. See, I'm moving the triangle with my mouse. I can click it, but I can also drag it. Now, when I right-click, okay, nothing happens when I right-click. I haven't put any code to make it do something when I right-click. But when I left-click, notice not only does the triangle move, but the colors change as it moves. Now, there's many different color modes. So let me show you solid color mode. Now, I can change the solid color. We have blue, green, cyan, red, magenta, yellow, white, and even black. Now, what's nice is there's a checkerboard behind this, so you can see how it is. So, okay, let's make it magenta for fun. Now, let's change this. Now it's it's a multicolored red, green, blue triangle. And that's because each vertex of each triangle within this triangle has a different color. This is a slightly alternate one, predefined color schemes. But then this one is my most recent one, the one that changes depending on the position on the screen of where the triangle is. It automatically changes the colors associated with it. Now, you might wonder how that works. Well, I'm going to show you the code, too, behind how some of this works. So I can change the size of the triangle as well by middle-clicking with my mouse. I could have made a right-click, but I was fancy and decided to make it middle-click because I don't know why. So anyway, now if I press X, it will then go through the progression. So it'll change into a square. And notice that you can see, like if I go to solid color mode, it just looks like one shape. But when I actually use one of the other modes, then you see that each shape is made up of multiple triangles. So that's the beautiful thing about this. You can do some incredible things. The possibilities are just endless with what I can do with OpenGL. But there's various other modes too, like it's hard to see that though. That only does the lines, but it's really hard to see on a checkerboard background. So you've seen that I have the ability to make strange color changing things. very bizarre. And it depends on what keys I press and what it does. Now, I'm going to set it back to a triangle. And what I'm going to do is, to anybody who's interested in computer programming and wants to get started making shapes like this, I'll give you a few pointers, okay? So first of all, there's several files in this project. There's several files here. Now, this is simply a file about that I had just written notes to myself. But I'm learning modern OpenGL. I've done some legacy OpenGL, but this is the modern stuff. So what I'm going to do is, first of all, let me make sure my screen is still going. Yeah, it's still going. Nobody's watching. Nobody cares about my programming. Okay, so let's open the main.c file. Now, there's a whole lot of code. So let's go to the beginning. So we're including several. We're including standard headers from the C standard library. We're defining the glue static constant. I had to do this to get things working. It's because we're going to be static linking with the glue library. And I'm running on Ubuntu Linux. We're using glue, which is the GL extension wrangler for modern OpenGL. It's new functions. And then I'm using glf3w.3.h. I'm using glfw, I think it's like GL framework, whatever, for using OpenGL. And then you see all these variables, every single variable has its purpose. This is some crazy stuff. I hope that you can see it. In fact, what I may do is I'm going to go back to my screen here, and I'm going to switch to making it just show the screen and not show me, in the hopes that you'll be able to see more of what's here. So here's the thing. I have all this code, like the polygon side and the step. This is important for star polygons. And I have comments here, the center X and Y coordinates. So you saw what the program can do, but now this is the part where I explain some things. So all these variables that keep track of different parts of the polygon. And then there's the shader programs as well. And I don't know much about the shaders, how that really works, but I have working shaders that I stole from a tutorial somewhere. I actually took 2 different tutorials and combined the shaders of each. I did some weird stuff. So, like, I'll go to the shaders file. See, this is a short file. This is my vertex shader source code here. This is my fragment shader, and it's simply, it takes the position and the color are actually from arrays. And I'm going to show you approximately how it works. Okay, so I'm not going to be able to explain this all. If you're new to programming, if you're new to modern OpenGL, you're not going to understand most of this stuff. But this states that I'm doing version 3.3 of OpenGL. It's compatible with forward versions in future instead of backwards with legacy, and doing core profile instead of compatibility. Compatibility is for older stuff, and this creates the window. Says has modern chassis OpenGL. That's why when I compile it and run the program, the title of the window shows up here. So it's cool, and then the program works as normal. But you might wonder, how is it that I press certain keys on the keyboard to get things to happen? I'll get to that. So it creates a window, and it sets, then we make the GL context, OpenGL context, be associated with that window. And here is where we set up the code for glue, which loads the modern functions, which includes the functions for the shaders and all this crazy stuff that didn't used to exist in OpenGL. So here's the callback functions. The callback functions are the most interesting part. So we have a function that's going to be called when when I resize the window, when I press a key on the keyboard. This is this function. This function is when I click a mouse button, and then whenever the cursor position changes, that while the mouse is clicked, I think, or even whenever it changes. So these callback functions do various things, and I'm going to show them. So it prints what the OpenGL version is. You might notice in the terminal that it shows it's the 4.6 port profile. And Mesa is the OpenGL implementation in Linux systems. So this is just the very start of the program, right when it starts up. We're setting up, it's generating vertex arrays and a vertex buffer. And I don't understand all this, but there's a vertex buffer and there's a vertex array. And here is what I stole from a tutorial where it has the variable, accesses the variable position here and the variable color here. So you'll notice in the shaders, there's position and there's color in the vertex shader. And those actual colors and vertexes are actually in an array. So it's creating these buffers, and then it's so it's enable vertex attribute array. I don't understand what all this means. They have various meanings. It works. That's what's important. Now, and the GL swap interval. This to control its speed. Now, if it's set to 0, there should be like no delay. It's way too fast. You see how fast the program runs so fast that you can't even see what's happening. It's just too fast. So, but when it's 1, it's just like 1 frame per second. Now, if I set it to 2, it will slow it down a little bit. You see how it slows it down? But the normal speed is with the GLFW swap interval set to 1. That's the way it is. Now, here's the thing, the position of the polygon. It starts on the center of the screen. That's because the width and height variables, keep in mind the width and height variables are defined at the top of the program here. And they can, of course, always be changed. But it takes the current width and the current height variables and divides them by 2 to get the center. And then it sets the radius equal to being the height of the window divided by 2. So it's very strange. Now, and then here's the main loop. After it sets up the Polygon function, there's actually a function pointer that points to certain things. This is crazy stuff. Here's the main loop. So it's drawing the checkerboard. It clears the screen, then it draws the checkerboard, and then it draws the polygon. Now, I'm going to show you, like, if I don't clear the screen, let's see what happens if I don't clear the screen. It still behaves normally because it's still drawing the checkerboard. But what if we don't clear the screen, nor do we draw the checkerboard, but then we draw the polygon? You see what it does there? It's freaky, man. It's like just freaky, dude. Whoa, dude, that's cool, dude. I did not see this one coming, man. Oh, that's cool. Yeah, I like this. Yeah, I love this, man. This is oh, that's funny. Yeah. So see, this is why the screen is cleared, because if you don't clear the screen, funny things happen like that. So anyway, so how about we clear the screen, but then we cancel out the checkerboard drawing. Then you see how it is. It draws the polygon, but not the checkerboard. So everything is very weird how this is. But anyway, let's put this back the way I had it. Yeah, so now it works. So I'm going to explain. You see that it does these things, but how is it drawing the shapes? How is it drawing the checkerboard? And all the variables, there's a lot of math. I could never go into all the math. I've tried to describe parts of it in my previous videos, but everything changes. The rotation of the regular polygon changes. The frame number changes here, and the frame number is only used to control 360 frames, it tries to increment the step variable and make a new polygon. So it cycles through every possible star polygon. That's what it does. Now, and that can always be changed as well, because there's a polygon change variable that determines whether or not it actually changes the shape. And so by every single frame, what it's doing is it's clearing the screen, drawing a checkerboard, drawing the regular polygon, updating variables, and then it's swapping the buffers, and then it's polling for events. And the events are all the mouse presses and keyboard clicks. And then after this, right here, see where this line 145, this is the end of the main loop. So as soon as I press escape or I click the X in the window, the program will end. And so it just cleans up. It deletes the vertex arrays and buffers, and then it terminates everything. So that's what it does. Now, as for how things are working, that's what I'm going to get into. I'm going to go into the callbacks function. I have a separate file just for the callbacks. So here, every single key that can be pressed is all defined here. So when I press the keys 0 through 7, it sets the color variables. I have global color variables defined at the top of this main program here. And it simply changes what the colors are of those variables depending when I press those. Now this polyfunc is actually a function pointer. And these keys change which function that that polyfunc is pointing to, because there's various different things, and this controls the color scheme, whether we're doing solid, whether we're doing my red, green, blue, whether we're doing cyan, magenta, yellow, and then my newest one that's just massively color changing all the time. Oh, and the polygon can be moved with the keyboard. So like if I start the program again and I do H, yeah, I see I'm moving left. If I do J, it goes down. If I do K, it goes up. And if I do L, it goes right. It's based off of bin. It's really weird how that is. Yeah, and Z makes the polygon change variable be 0, so it won't change. And it changes the number of sides to 3. So it's weird how that is. In fact, yeah, that's weird. Anyway, yeah, it works. So that's all of the key presses. I have to put custom code there. And then the mouse clicking things, like it gets the cursor position of the X and Y variables, and then it sets the new center X and Y variables of the regular polygon to equal whatever I left click. And the middle mouse button does a simple formula of the polygon radius to how big the polygon is the X plus Y values. So there's a reason this happens. So if you see, if I go up here, it gets smaller. If I go down here, it gets smaller. But if I go to the right, it also gets bigger. So it's weird. So I can completely customize just by middle clicking on different portions of the screen how big I want the polygon to be. So everything can be controlled that way, position and size. So this is basically the same thing, except this is when the cursor position changes. Then it gets the state of the mouse button if it's left click, or the middle button, it does the same thing as what the above one does. This is the frame buffer size callback. So whenever the window is resized, it sets the width and height variables to be the new width and height of the window. It sets the viewport to be the GL viewport is a weird thing, but basically if I do this, it resets everything the way it should be. Then it recenters where the polygon is. And another thing is, it's weird. It doesn't let me scroll down to add from blue line just for it to let me scroll down. You'll notice that it changes depending on whether or not the width is greater than the height or not, and you'll see what I mean. So when I run the program, it will, you see, it makes it so that the size is based off of the width here. But then, then when I do this, it's based off of the height, because the height's smaller. But so as soon as we do this, yeah, it's strange. So as soon as one dimension gets smaller than the other, then it changes which dimension the polygon is based off of. And so it's auto resizing. It's so cool how that works. But yeah, I mean, there's so much. This is massive. But for the final thing I want to show in this video, I want to show exactly where is the code that is actually doing the actual drawing. Okay, so I'm going to show you. Now, you'll notice that it's calling certain functions in the main event loop here. The core checker and the poly func is what it's calling. So here's the thing. So now let me go back to my editor, my Explorer here. So this is the biggest file in the whole project. So here's what it's doing. There's so many functions here, I don't even know where to begin. So these are my ortho functions. It takes the orthographic coordinates that I'm used to, like in my legacy OpenGL days with GL ortho, which doesn't exist in modern OpenGL. So these are functions to convert orthographic coordinates into normalized coordinates, where everything is between the range -1 to +1 for position. So I had to write special functions. They're not very big function. It does a simple little conversion. That's all you need to know for that. This is the first get polygon points core function. And here's what it does. Now, each vertex, according to my shaders and my array buffers and all that stuff, is set up in this following manner. It's a two-dimensional system such that each group of 5 floats defines a single point. So here, it's going through the loop based on the number of sides of the polygon. And it sets up the angle based off of the polygon radians and the sides and all that of this particular angle at that point. Then it sets the x and the y position, calling my above functions here. It uses those functions to make sure they're properly set. And then it uses the global variables after that to set the what the red, green, and blue values are of that specific vertex. Now, when you saw me run the program, you'll notice that it had all sorts of gradients of moving from one point to another. It slowly changes. That's one of the great things about OpenGL is you can do that by assigning each vertex of a shape to have a different color, and that's how it works. Now, this one is a little bit interesting because, this is the GL polygon function. Now, this one draws a solid polygon. It does a triangle fan is what this one does. And I need to do more research on what all these different things mean. All I know is this is what got it to work at the time. I liked the way it was here. And this one, yeah, this does a fill regular polygon. This one does only the lines, but doesn't fill the polygon. This is the first of the star functions. This gets the points, and here's how it works: is for each of the sides of the polygons, it does a very weird thing. It's actually drawing a whole triangle. This is for each 3 corners. So it takes the center position and 2 different corners, depending on the step variable of a triangle for each iteration of the loop. So a 5-sided star, a pentagon with a step of a pentagram that has a step of 2 and then polygon sides of 5 is going to be made of 5 triangles drawn over on top of each other. And this is the same thing, but you might wonder, well, why do I have each vertex color as part of this array? Well, the reason is because it's so easy to customize. This one is the one that does red, green, and blue all the time. And you see that the colors are set to 0 and 1. So red, green, and blue. Red is 1 here, green is 1 here, and blue is 1 here. So it has to set up all those variables for those triangles. And this is the same thing, but slightly changed color. I copy paste my functions and then modify them. This one is the mysterious one. And you'll notice something. This is the default one that I use. When the program starts, it's calling Polygon 2. And this is this is a function pointer that points to the above function here, or well, it does here, but it gets reset. So by changing the function pointer, which color scheming function and which vertex setting function, that's why my program is so powerful and can change to all sorts of various situations depending on mouse and keyboard input. So Polygon 2 is the one that I use the most. It gets the current function. You'll see, like, okay, when I run the program again, so you'll see what it's doing here. It has all that, but this is changing which of those Polygon functions is used, is what happens when I do that. This one is my favorite, and you'll notice that in my main .c file, just before the main loop begins, that I set it to Polygon 2 is the polyfunc, and get Polygon points array star func equals this. That's the tricolor one. So it's setting what the initial state of those Polygon functions is. So it can change various things. So that's the whole idea. So anyway, yeah. So there's a whole lot of code that goes into this OpenGL stuff. Now this checkerboard function is the one that I just did today. I just wrote this function today. And so you'll see that, of course, it does draw a checkerboard. But things can be changed with the checkerboard. First of all, the rect size can be changed. So let's say I want to make the squares be 64 pixels width, wide, and high. I change the rect size to 64. Notice how the squares are bigger? That's because they're all defined by the global rect size variable. So that works. But I can do more than that. See this? These are actually local copies of the global variables. They have the same purpose, but they are only defined in this function. So it does the same process. We are converting the orthographic to normalized coordinates for the x and y position. So it's actually, each square is actually made up of 6 vertices. And that's because it's made of 2 triangles. Each triangle has 2. So the first triangle is this, this, and this. Second triangle is this, this, and this. So during each part of the loop, it's defining those 2 triangles. And then it is updating the try count, the number of triangles. It keeps track of that. And then it sets the buffer data here. And then it draws all of the triangles all at once. That's precisely what it does. Now you notice that it's black and white. The squares are black and white. I can change that just by changing the numbers here. It's not hard. So let's say I want to have, let's change this one to that. Now we have red and white. We can do that. We could change this to 0 in the second color. And then we got red and cyan. It's not hard to do that because the local color variables are changed. But I can also show you something else. Let's change this back to the way they were. So they're black and white here, okay? But we can get a little bit fancier than that. I can prove to you that the squares are made with 2 triangles. So here's what we're going to do. We're going to take these color declarations, and then what we're going to do is we're going to change it so that after the first triangle is drawn, then we're going to set these color variables. We're going to set this to green. Red 0, blue 0, green 1. So let's see what it does now. You see that? You see how it still has black and white for the other triangles? But the second triangle of each rectangle is then drawn with the green color. But it gets much weirder than that, because you can even do it between vertices of the same triangle. And that makes it really freaky. So like, let's say if we do it before the very last vertex of that triangle. You see, it's the only one of the vertices in that triangle is green. That's some weird stuff I can do here. So it's really impressive. And of course, keep this in mind. If I were to simply change the color to green before either triangle is drawn, then the whole thing just ends up green, because it's drawing only green squares, green triangles, basically. But you get the idea, basically. I have complete control over, just by changing the color variables, different little things happen. So anyway, yeah, I'm going to remove this, and I'm going to keep it, put it back to the exact way it was. But it looks like a lot of work, doesn't it? And yes, it is a lot of work. But the point is, this program really works. It actually does something, you know. So I can control the where the triangle is on the screen by various key presses. I can change the mode of drawing. I can change the solid color. But I can also go back to star mode. It's just nice. Yep, it works great. So yeah, I mean, it's taken me a long time to understand everything, but you see, this is how modern OpenGL works. You set up your array of vertices, including position and color. We have 2 position variables, and we have 3 color variables for red, green, and blue, primary colors of light. We set up all of those, and we just draw all the triangles at once. Now, this is one example where modern OpenGL is actually faster than legacy OpenGL, because with my legacy OpenGL functions, things were a little bit different. I'll show you my, I guess I can just quickly, before I end this stream, I can show you my legacy OpenGL code. My legacy OpenGL code for drawing a checkerboard looked a little bit different. Let's see here. Here we have, yeah, here it is. My legacy one is different. Everything was different. It uses GL begin, GL end, GL color 3F, GL vertex 2F. And this code is a lot smaller. It's a lot easier to understand. I still like legacy OpenGL more because it's easier to work with. Because here's the checkerboard function. This right here is the checkerboard function. Can you believe how small it is? Well, there's a reason for that, because in legacy OpenGL, there is an actual glRectI function that takes integer coordinates, and you can make rectangle just by calling a single function. You don't need a vertex array, you don't need shaders, you don't need none of that. So this right here, this block of code is my entire function of my checkerboard drawing function in legacy OpenGL. And you see how much smaller it is. I don't have to do all that complicated stuff. Well, that's why I like legacy OpenGL. Now, legacy OpenGL is a very different system than modern OpenGL, but it's just easier to work with. So my personal recommendation is that people do start with legacy OpenGL. But because it's just easier to work with. In fact, there is a tutorial I'd like to recommend. Okay, first of all, yeah. Oh, and what I can do is I can just really quickly, I'll run my program here. Now, I don't have the checkerboard enabled in this one, but this is my legacy OpenGL program running. And it's very similar. I can change the colors of some things. I can change various weird attributes of these things. Yeah, oh, and there's different modes too. There are different modes of what I can do. This is very similar. Yeah, it's cool stuff. It really is cool stuff here. Yeah, I like that. Oh, whoa. Yeah, but anyway, it's incredible all of it. But you can, in fact, write any program you want with legacy OpenGL. And the difference between legacy OpenGL and modern OpenGL has to do with shaders. It's some complicated stuff. I don't necessarily understand all of it now, but OpenGL is actually very interesting. Let's see, I'm trying to get to back here. Okay, so legacy OpenGL is easier to work with because it doesn't require shaders, it doesn't require vertex buffers or arrays. It's just easier to deal with. It's called an immediate mode. Let's see. So I'm going to do a little Google search. Immediate mode graphics. So there's a Wikipedia article on immediate mode graphics. Now, immediate mode Bureau says major ABI design in graphics libraries. So let's see here. There's a whole lot of stuff here. I know, okay, examples of immediate mode rendering systems include Direct2D, OpenGL, and Quartz. There are some immediate mode GUIs that are particularly suitable when used in conjunction with immediate mode rendering systems. Now, here's the thing here. Now, yeah. You see, modern OpenGL doesn't use immediate mode. It uses the whole shader system that I showed you. But Quartz, now, Quartz is using Apple Mac OS operating system. It's an immediate mode API used in the Apple computer operating system is what that is. Now, Direct2D is a 2D vector graphics application programming interface designed by Microsoft and implemented in Windows 10, Windows 8, Windows 7, Windows Server, blah, blah, blah. Now, so Direct2D, because it's an immediate mode thing, it's strange. So it's a Microsoft invention, this Direct2D. So it's different than OpenGL, a different graphics API. I've never learned how to use it. I would have to learn a whole tutorial, but let's see, how old is Direct2D? I'm just curious because I'm a computer nerd here. Yeah, it's native API based on C++. Yeah. Very strange. Yeah, I don't know much about that, but apparently it's existed for some time. Does it have a... Well, okay, so it's not in like very, very old versions, but all the modern Windows versions have Direct2D support. So when you do two-dimensional graphics, Direct2D is probably a pretty good idea. Use Internet Explorer 9 and later uses it. Interesting. Yeah, I'm just interested in the nerdiness because if I use Direct2D, I would be only able to write programs on Windows using it. But yeah, it is cool. So anyway, let me stop the screen share and go back to my camera because I wanted to just talk a little bit about this. So yeah, I followed LazyFu's tutorials on OpenGL. It was legacy, and then I got into modern stuff, and I completely lost it. Like I wasn't following it or understanding it at all. And one of the things I had a hard time with was getting multiple colors of triangles and other shapes using modern OpenGL because I didn't know how shaders work. I didn't know how to get the vertex attributes set up right. And so I've had to follow a lot of examples. But as you have been able to see in this video, I can get modern OpenGL working. So I've been working for the past 2 hours on computer programming. And I'm going to back up my files because it's amazing stuff what I've been able to do with this. It's great. But the checkerboard program was so much bigger in modern OpenGL than legacy OpenGL. And I still like the legacy OpenGL version because for the most part, although there is a speed advantage because there's fewer function calls in the modern approach to OpenGL, that speed difference is most likely not going to be noticeable if you have a very fast modern computer. So it's not always that important. Right at the start, if you are interested in graphics programming, there is actually a program called Basic 8. It's part of Steam. If you know Steam, the platform for games, there is a basic interpreter called Basic 8. I used it a little bit. People actually make games. It's a dialect of Basic. I highly recommend you try that out because what I like about that is if you have Steam, if you have a Steam account, you play games on Steam, you simply buy it. It's like, what, $8? It's nothing. And then you can load the demos, you can look at the source code, and you can draw triangles and rectangles. So in the future, I might even do a video on some of that. It's been a long time since I've used Basic 8, but on my Dropbox, I have a few programs that I wrote with Basic 8. I'm not very good at it though, mind you, because I'm used to the C programming language. I was using the C programming language in this video, but when you're dealing with interpreted languages like Basic or Perl or PHP or Python, programming is easier. Programming is easier in interpreted languages for a reason, because the interpreted languages do a lot of work for you. So they would for creating a window and setting up an OpenGL context, like the libraries would just do that for you in some cases. You don't even have to know what shaders are. Instead, in fact, I would say that using Basic 8 or Free Basic or QBasic, because QBasic was my favorite, it was my favorite programming language. It was my very first programming language. If you've done DOS programming using QBasic back in the really old days of Windows 95, 98, even prior to that, then they actually had functions like triangle, rectangle. You could change the colors. You could draw two-dimensional shapes using QBasic. And that was back in the 80s and 90s. You could do that. That was immediate mode because you're just calling a function. That function executes the code to draw a shape on the screen. Immediate mode is called immediate because it's fast. It's easy to learn. It's easy to use. So in the future, I do hope to cover more graphics tutorials, I suppose, because if people want to get started drawing shapes, you have to know a little bit of math. But there's definitely an easier way to achieve it using modern OpenGL. But legacy OpenGL is good. Modern OpenGL is good and efficient, but it's hard to learn. So if you saw that code and you're like confused, like what is all this? Just know I've spent months learning this stuff to even learn this. And you might wonder, why did I learn something so complicated as OpenGL? Quite simply because it is cross-platform, because a lot of games are made using OpenGL on Linux systems, and I thought, hey, it's cross-platform, it's an open standard, and I mean that it's managed by the Kronos group. Kronos now owns the copyright to the API design of OpenGL, but the actual functions are made by the graphics card manufacturers. The Cherno in his OpenGL series explained this. The Cherno is a guy who teaches a lot of programming stuff on YouTube, and I listen to a lot of his stuff. And he is very helpful when it comes to programming concepts, and he's free to listen to. It's great. But yeah, so anyway, I guess that's all I really have to say for right now. Just so you know, I can provide a little bit of help. If somebody is looking to get started on drawing a shape to the screen, I might be able to help in certain ways, but there probably are easier APIs to start with. But I do still recommend OpenGL because it's possible to running on Windows or Linux. I even got an OpenGL example compiled and running in Visual Studio on Windows. And I had to follow a video example of the Cherno to get it to work. I still don't understand it, but I just did everything exactly step by step. in the video without understanding all of it, but it works. So I can compile and run that program on Windows using Visual Studio, but it might actually be easier if I just installed a Linux environment within Windows like MSys or Cygwin if I really want to do OpenGL programming in Windows. But I don't really feel the need to. But if I ever make a game, then I'm definitely going to compile a Windows version so people can play it. Because most people aren't running Ubuntu Linux. But my friend who runs a Minecraft server is running Ubuntu Linux just like I do, and that is super cool. He's kind of a smart computer guy. I like him. Anyway, that's what I got to say for now. I hope somebody has enjoyed my long programming rant and demonstration of drawing my various shapes.